Okay, hello everyone. So today I'm going to attempt this Codeforces educational round 102 and it has already started. So before we begin, there are some small announcements. So first of all, subscribe to my YouTube channel if you haven't already subscribed to it. And hello. Okay, yeah. So apart from that, join my Discord server because I do a lot of announcements and suggestions and everything there. Okay, so make sure you don't miss that. And if you are a Hindi speaker, then check my description. There's a link to a graph theory course that I recently did on an academy. So it's free of cost, but if you want to access it, you can do that by going to the description. Anyway, so let's start the contest now. We're at problem A right now, replacing elements. Okay, so we're given an array and all values are positive. And in one step, we can choose three distinct indices and make one of the elements equal to the sum of the other two. Okay, can we make all ai lower equal to d using the operation above any number of times? Okay, so yeah, that's the question. Can we do this, right? So I think we can use the same j and k all times. Okay, so just we want the smallest two elements. Like if the sum of the smallest two elements is smaller than d, smaller or equal to d, then we can do it. Otherwise, we can. All right. First of all, we have some test cases. Okay. Then we have n and d. Okay. Now we have the array. We want to input the entire array. Typos. Anyway. So we've input the array. Now we can sort the array. Okay. After sorting the array, let's say s equal to a0 plus a1. Okay. These are the two smallest elements. Okay. Now, if s is smaller or equal to d, then the answer is yes. Okay. Otherwise, it is no. Okay. Let's first check it on the sample. Hmm. Okay, so I think it's wrong on the sample. Let me see. Hmm. Okay, there's one exception. If all the elements are already smaller than d, then also it's fine. Okay. So if this is true, or the greatest element is already smaller or equal to d, then we can do it. Okay. Okay. That's that. So this was simple. Like first of all, if all elements are smaller than d, smaller or equal to d, then we can obviously do it. It's accepted by the way. And if there are not all smaller or equal to d, then what we can do is we can replace all the elements that are bigger than d with the sum of the smallest two elements. Okay, so we can preserve those two smallest elements and we can change everything else accordingly. If that is smaller or equal to d, then we've done it. Okay. So we've solved one problem right now and we're at problem B now. Okay. So let's define a multiplication operation between a string A and a positive integer x, ax as the result of x copies. Okay. Okay. So ABC into 2 is ABC twice. Okay. A string is divisible by another string if. Okay. 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 Fine. So it's divisible if we multiply some number to this string and we get this string. So uh, A is divisible by B if A is like a repetition of B any number of times. Okay, fine. So LCM of two strings is the shortest non-empty string that is divisible by both S and T. Okay. Okay, cool. So they've defined a lot of clumsy things, but what let's see what we exactly want here. So we want a string. We're given two strings as input, and we want one string such that it is divisible by both of S and T. Okay. So okay, it might not exist. So if it doesn't exist, we can just print -1. But if it does exist, then it should be the repetition of both S and T. Okay. So I think maybe hmm, I guess we can just start with the smallest string, right? So it should be a repetition of the smallest string and also the repetition of the biggest string. Okay. I think it's just the LCM of the lengths, right? So like this, the length of this is 4 and the length of this is 2. So the length of LCM will be like the actual LCM of these two, so which will be 4. And if we make it because like it cannot be smaller than that, right? And it must be a multiple of it. So I think that's what the answer is. In this case, we know that it cannot be done, so it's -1. That's obvious. Here the LCM is 6, and we have the and 6 here. I think that's all we have to do, right? Hmm. Yeah, I think that's it. Okay. And since these lengths are very small, it's we can just do it naively. Okay. So yeah, test cases. Then we have two strings S and T. We input S and T. Okay. So that much is done. Now let's take the length of S and length of T. Okay. Now let's say the length of the answer string is the LCM of these two. So it will be n into m divided by the GCD of n comma m. That is the LCM. Okay. So we want two strings like capital S and capital T. Okay, and these will be like the repetitions of these that like Z characters. Both of them will have. Okay. So they both should have Z characters, right? I'll do S dot pushback. I think SI mod N, I think. Okay. And in T, it will be TI mod M. Okay. Now, if S is equal to T, then I think S itself is the answer. Okay. But if it is not that, then let me just print -1. I think we've got it. Okay, so at least it ran on the sample. Let's submit it and see if it's correct. If it is not correct, then we will try to fix it. Okay, it's correct. So no need to fix it. Anyway, now we're at problem C. In problem C, we are given a sequence with n elements. Okay. And what? 1, 2, 3, k minus 1. Sorry, k minus 1, k, what? Uh, hmm. I don't really get this sequence. What is it? Like, let's say k is 10. So, first of all, we count from 1 till 10. Then we keep on decreasing it, right? Till we reach 2k minus n, I think. Is this 2k minus n? Okay, cool, cool. I think I get it. So we have k elements here, like we have 1 to k elements here. Then we have k elements here. So like this is from k minus. Okay, sorry, yeah. So we have k elements here from 1 to k. We have k elements here till this point. Okay. So from 1 to k we have k elements. Then from here till here we have n minus k more elements. So it is like k minus 1, k minus 2, dot, 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 k minus n minus k. So these elements are n minus k in total. Okay. So anyway, and since k is in n is in this range, I think this will never be negative, right? Yeah, because this is 2k minus n, and yeah, that will always be positive. Okay, so yeah, all the elements are positive. Anyway, so we call an inversion as a pair of indices I comma j such that okay, yeah, that's the standard definition of an inversion. Suppose you have some permutation p of size k, and you build a sequence b of size n. Okay, in the following manner. What is this? Okay, so let's say we already have a permutation and we do this thing. I don't I don't know the physical interpretation of this. Let's just say we do something like this. Okay, so my goal is to find permutations such that the number of inversions in B doesn't exceed the number of inversions in A, and B is lexicographically maximum. Okay, small reminder: the sequence integers k is called permutation k. Another small. Okay, okay. Are we just given n and k? Okay, yeah. So we are given n and k, and using those we can generate this sequence. Okay. Okay. So let's see what that looks like. Okay. So let's say k is equal to 10 and n equals 12. Okay. Now let's see what that actually looks like. So we'll have elements like 1, 2, 3, 4, dot, dot, dot till 10. Then we'll have 9 and 8, I guess. Okay, so now I think I get it. We have n elements, and till 10 they are till k they are increasing one by one, then they start decreasing one by one. And so this length is k, and this whole thing is n. So this thing is n minus k. Okay, I get it now. Now what we want to do is we want to convert uh, mm, right. So we want to convert that into a permutation, I think. No, so we already have a permutation, then we change the elements according to that. Okay. So it's like, okay, so I think the elements will be converted based on the height, right? Like if we make it like this. Okay, so since these two elements are equal, these two are equal, these two are equal, and so on. So if we change this, this will automatically get changed, right? Okay. We want the lexicographically maximum string B, sorry, lexicographically maximum sequence B. Okay, and the total number of inversions in it should not exceed the number of inversions in A, and we want to find such a permutation P. Okay, so first of all, let's see how many inversions are there in this thing. I think it can be calculated in O1. So inversion means an element at a smaller index is greater than the element in the bigger index. Okay, so for this element, I think we add n minus k. So here we add n minus k, here we add uh, I think n minus k minus 1, okay, and so on till this point. So I think it's the sum of all the numbers from 1 till n minus k. Now this sum is equal to n minus k into n minus k plus 1 by 2. Okay, so we already know the number of inversions in this thing. Now we want to convert this into like graphically maximum, right? Maybe we can just put a k here. Like, what's the disadvantage of putting a k here? Like, map this index to a k. Will that be wrong? And if yes, then why? If we have a k here, wait a minute, what if n equal to 5 and k equal to 10? Like, k is the exact double of n. Let's see what will happen in that case. So we'll have like 1, 2, 3, 4, 5. Then we'll have 4, 3, 2, and 1, I think. 5, 4, 9. I think then, okay, yeah. K cannot be equal to the double of n. Wait a minute, I'm doing the opposite thing. Actually, if k is 5, uh, okay. So if k is 5, then this can be up till n. Okay, fine. So the first element can be twice, till twice, like it can be like this mountain, okay, but not worse than that. Okay, so this won't go below this. Fine. So if we make this element equal to k, then what will happen? Then all of these have to be smaller than that, right? And how many elements do we have here anyway? So here we have, I think, we have k minus 1, and this is everything else except maybe this one. Okay, so we have like n minus 1 elements here in total, but if n is equal to 2k, then we have n minus 2 elements there. Okay, so I can't say if this value is greater or smaller than that. Moreover, if I wait a minute, I think there were more inversions there because even this element is greater than all of these. Okay, so right, we had n minus k inversions here. Then we had this should be doubled because we have those here and here both. Then here and here both, and so on. So we can remove this by 2. Maybe we can subtract this n minus k. Right, and if we take n minus k common, I think we always have n minus k inversions in this, regardless of the thing. Okay. Hmm. Hmm. N minus k inversions, right? So n minus k square. So I think here we should have only one inversion. Okay. Okay. So, yeah. So I think this is correct. Okay. So the bottom line is we always have n minus k square inversions. Okay. Now how can we rearrange the sequence so that I don't have more than n minus k square inversions in the sequences that graphically maximum? Okay. I think we had something like this, right? Now, what can we do? The thing is, if we put a big element here, then these type of inversions will be added. But if it was all the way till here, and if we had put a small element here, then what would have happened? Then I think even these inversions are getting added. Like if this is small, then everything has to be added here, right? Mhm. So, is it like a constant or something? Maybe in this hill part it's constant. It doesn't matter what I put where. Okay, so like so this is what I'm saying. Let's say it's a hill like this. Okay. Now if I put X here, okay, so all the elements that are bigger than X, they are somewhere here, right? So they are all adding to an inversion. And then X is here as well. So all the elements that are smaller than X, they are also here somewhere. Even they are contributing towards one inversion. So what that means is, um, right, if there are supposed to be like E elements here, so so like E elements will be there and E elements will be here, right? So some will be smaller than this, and uh, they'll give us an inversion this way. Sorry, this way, and the rest will give us an inversion this way. Right, so in this peak part, I think the number of inversions are constant. It doesn't matter which elements we're using, right? Because for this point, sorry, so it depends on the number of elements like this, I think. Hmm. Maybe it matters what goes on the top because the peak is unique. Hmm. Figure this out. Hmm. Okay, then something has to go here. Okay. Okay, so fine. I'm pretty much convinced. So in this symmetrical mountain part, the number of inversions are actually constant, and it doesn't matter like where we start. Okay. So in this part, depending upon whichever elements we have left right now, okay. So like the thing will always be like this, right? So we'll put some elements here, and then some will be left for this part. So we'll always put the remaining elements in descending order here. Okay. And we'll do that because like we'll do that because the number of inversions are constant no matter how many put elements here. Okay, so let's try to see how many elements will be here, how many inversions will be here. Okay, so we'll divide this here, and let's say the okay, so this was k, sorry, yeah, this was n minus k, right? This was n minus k, and this was also n minus k, because that's why the mountain is forming. Okay, so this is 2n minus 2k minus 1, I think. Hold on. K minus n minus k. 2k minus n. This one, the 2k minus n, minus 1. Okay. Uh, hmm. You don't need to figure out the exact math. Let's leave something for the computer. Okay. So let's say we have e elements here, then one element here, then again e elements here. Okay, so we can calculate the exact number of inversions that will be there, because for each element we will be having the double of all everything else, and then like one element will give only one inversion and everything else will give two inversions. Okay, so yeah, that much the computer can figure out. Apart from that, we extend this. Now we want to, like, we have constant number of inversions here. We want to optimize it in such a way that the number of inversions here plus this do not exceed our total count, which was n minus k whole square. Okay, and let me just look at once more. How is it n minus k whole square? So this part gives no inversions at all. So all the inversions come from here, and if we have like n minus k inversions here, okay, sorry, wait a minute. Wait a minute, yeah, okay. This part gives no inversions, right? And the inversions here are constant. So we just have to kind of sort these elements in the reverse order, and they should remain the same. Okay. So maybe like till 2n minus k elements do nothing, and sort these and accordingly reverse sort these. That's all we have to do. Yeah, I think that's exactly what's happening in these. Wait a minute. So we have 3, 2, right? 3, 1, 2, 3, and k is 2. Okay. Okay, so this was like this. And 4, 3 is like 1, 2, 3, 4. Okay. It meant that leave this one, then sort these two in reverse order. It will be like 1, 3, 2, 3, I think. 1, 1, 3, 2, 3. Okay, so we don't have to do anything with this 3. We just have to print the permutation, right? So we just messed with the last elements, I think, and leave these. Okay. So let me figure this out again. We have like 1, 2, 3, and we have something here. So these are n minus k elements here. We have n minus k minus 1 element. So we mhm. Wait a minute. Wait a minute. If these are n minus k elements, okay, these are also n minus k elements, and this adds another one. So this is n minus k plus 1 elements, and we have to subtract this from k. We have k minus n minus k plus 1 elements, that is equal to 2k minus n plus 1. So we don't touch these many elements and we sort the remaining. Okay. Let me just check it on that simple. Where k was equal to 2, I think, and n was 3. So this is 4 minus 3 minus 1 equal to 0. We don't check 0 elements, we sort the remaining. And then this was 8 minus 3 minus 1. And that was equal to, no, this is wrong. Okay. Yeah, sorry. Okay. 6 minus 4 minus 6 minus 4 plus 1 or minus 1? Yeah, this is minus 1, I think. Okay. Sorry, 1. Okay. So bottom line is we don't touch 2k minus n minus 1 elements, and we touch everything else. We reverse sort everything else. Okay. So test cases. Okay. So untouched elements are 2 into k minus n minus 1. We don't touch these many elements. Let's just print them in the proper sequence. Okay. We just print them in the proper sequence like this. Okay. This will be like 1, 2, 3, 4, till u. Okay. After that, we have k minus u more elements. Okay. So we have till u plus from u plus 1 till k. Okay. We'll put that in a vector. We can just, I think we can just print those in reverse order. It doesn't matter. Okay. For int j, for int I equals k, I is greater equals u, and I minus minus. So we'll just, sorry, I is greater than u because we have printed till u. Okay. And we'll just print I again and leave a space. Then we'll leave a new line. Okay. What this is, so this is k minus 1, k minus 2, dot till u plus 1, till u plus 1. Okay. So basically this is what we're printing as the answer. And okay, so this is correct on the samples. Let's run it. I think we wasted a lot of time. Yeah, 400 submissions already. Never mind. Did we get it? Okay, so it was correct. Anyway, so we're at problem D right now. Problem D is you are given a program that consists of n instructions. Initially, a single variable x is assigned to 0, and afterwards the instructions are two types: increase x by 1, decrease x by 1. Wow, okay, that's simple, I think. Wait a minute, let me just clear this first. Okay, let's see. You are given m queries of the following format. Hmm. Hmm. Okay, so we have like some additions and some subtractions. Okay, then we ignore some one interval in a query. Like we can ignore everything here. Okay, so we want to tell how many distinct. Okay, Okay, I think I'm getting the question a little bit. Let me just read it and understand it more. Okay. Leave this one out. Hmm, plus 1 minus 2 minus 1 minus 3 minus 2. Okay. So plus 1 and minus 3. So plus 1 0 and minus 3. This answer is 5, I think. Oh, 4. Hmm. We leave 1. Then if we leave 1, then we have plus 1, then we have minus 1. Okay, 0 and minus 1. Then again 0, minus 1 and minus 2. So we have minus 2, minus 1, 0 and 1. So we have 4. Like, okay, so I think I understand the question now. Okay, okay, I get it. So it's something like we're given a sequence of plus minus operations. Okay, these operations mean either add or subtract the element, and we want to count the total number of distinct values that x attains. Okay, so like if this was the sequence and x was equal to 5, then it will be like initially it was 5, then it becomes 6, then 5 again, then 6, 7, 8, 9, and then again 8, 7, 6, and 5, right? Okay. So we want to count the number of distinct values in this. So they are 5, 6, 7, 8, and 9. Answer is 4. Something like this we have to do. And for this, what we're doing is, I think we just, let's say for each, like we move from left to right, okay? And for each plus we add 1, and for each minus we subtract 1, okay? So here we have the balance equals 0, then here we have 1, then 0 again, then 1, 2, 3, 4, 3, 2, 1, 0. Okay, and we just take the maximum and minimum from this. Okay, so maximum is equal to 4, minimum is equal to that minimum. Minimum equal to 0 and maximum equal to 4. Then my answer will just be maximum minus minimum. Okay, that will be my answer. So that's what I have to do, but the queries are strange. In the queries, I remove a certain part. Let's say I remove this part. Okay, cool. So if I remove this part, then I have this part and this part left. Okay. So what can we do? Can we? I think we can just use a segment tree here because we know the total balance and the maximum balance till this point. Okay, so at least for this interval, we don't even need a segment tree because, like, we already. I think we already have it, right? What I mean to say is, we already have this thing. We can do a prefix sum for this. And I think this will be a bit tricky. Can we do it from the other side, the prefix sum thing? No, I don't think we can because we want the minimum on this side. Okay. So, maybe we just need the minimum and the maximum prefix in this range, right? And then we will just subtract this part. It should work. I just want the minimum and maximum prefix in this range. Okay. So if I take the minimum maximum prefix in this range, it will definitely work. And if I take the minimum and maximum prefix in this range and subtract the value here, like this value is, I think, 1 plus 1 minus 1 equal to 1. If I subtract 1 from all these, will that work? So it will be 1, 0, minus 1. Will that work? Let's see. If we start here 0, 1, 0, 1, 2, 1, 0, minus 1. Okay, yeah, it's working. So yeah, we just need to make a segment tree on the prefix sum. Then we will use yeah, I think, and yeah, that's done. Then we will just use we want the segment tree on the prefix sum, and we want the minimum and maximum prefix sum. Okay, so we will just first build the prefix sum. Then we want a segment tree that gives us the max and the min both. Okay, so we can either make two different segment trees. I'll do it in a single segment tree. Okay, after that, from the value we get, we'll subtract this part, the removed part. Okay, so we should be able to get the sum of the removed part as well. For that also, I can use I can simply use the prefix something, and then yeah, and then we're done. Okay, so this is an easy problem. I mean, it's not very easy. It's a bit standard. So if you know things about segment tree, then it's easy for you. Otherwise, it's not very easy. So anyway, okay, so we have the segment tree. The segment tree stores the maximum and the minimum. The maximum, let's initialize that with minus infinity. The minimum, I'm initializing it with infinity. Then in the constructor, everything is equal to value. Then the minimum is actually the minimum of both children. Okay, the maximum is the maximum of both children. Sorry, minimum is the minimum. Okay, yeah, let me do this silently. Need to concentrate a bit. Okay, and yeah, I don't need any updates. I just need to resize it a bit, I think. Okay, so do I have test cases here? Okay, I have cases here. Fine. Now, yeah, N and M. I think M are the number of queries. We have N and M, C and M. Okay, and I also have a string, I think. Okay, so let's call it string S. Put that as well. Now I need something for the prefix sum, right? Let's make a vector of size n plus 1, let's say. Okay, so we'll use this for prefix sum. Let's set the length of segment tree also equal to n. Wait a minute. Let's set it equal to n plus 1. Fine. Now, okay, yeah. Okay, now we want to store the values in this prefix sum. So okay, so vi is equal to vi minus 1. Okay, plus okay, I'll use the ternary operator here. So if si minus 1 is plus, then I'll add 1. Okay, otherwise I'll subtract 1. Okay, so I think that's done, and we have the prefix sum built. Okay, now let's build the segment tree using that. I think I made the function correctly. Okay, sure. Right, so I cleared the segment tree because there are a lot of test cases. Finally, I need to build the segment tree on this prefix sum that we made. Okay, right. So this segment tree is a very personal kind of thing. I've made it on my own, and I use it in my own way. You can use any segment tree that you use. Okay, now we have M queries. In each query, we have L and R. Okay. Okay. Now we have to divide it as two intervals. One interval is 1 till L minus 1, and the other interval is R plus 1 till n. Okay, so that's what it is. So the first interval will be valid. Okay, so let's make two variables, mx equal to minus infinity and mn equals infinity. Okay, so first let's go into this interval, right? So we'll go into this only if L is greater than 1, right? Yeah, because if L is equal to 1, then this interval is non-existent. Okay, so we'll go into this if it is greater than 1. Then what we will do, we will do t dot query from 1 till n minus 1. Okay, auto temp equal to this thing. Now I want the maximum to be max of mx comma temp dot max. Okay, maybe so these are actually functions that are pretty much made by myself. If you're using your own segment tree, you can use things that you use. Okay, so this will go into this if r is smaller than n, because otherwise it makes no sense. Okay, now again auto temp is equal to t dot query till r from r plus 1 till n. Okay, so do we use these two functions again? Actually we can't, because we have to add the actually we have to subtract the balance, the changed balance, right? Okay, so what's the balance? Let's try to see what the balance is. The balance is the sum of the removed part. Okay, the sum of the removed part is simply vr minus vl minus 1. I think it's just vr minus I think this is the balance, right? Wait a minute. So if you want the sum of the element, okay, yeah, this is the balance. I think we got the two things, the mx and mn, and we just have to print mx minus mn, and that's it. I think we've done it. So let's try to run it on the sample case. Is it working? Okay. So yeah, so this one failed. I think it had failing a bit. Hmm. 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 Okay. Okay, I think there's one exception. Hmm. Hmm. I think 0 will always be there, right? So maybe we can just start with 0 here. Because like 0 is always in the range. And then maybe we need to add 1 here, because even if it is 0, then we have one distinct, right? Okay, it worked now. I added this 1 because like if the max is equal to 2 and the min is equal to 0, then the answer is actually 3, because we have 3 elements, 0, 1 and 2. Okay, and instead of doing minus and plus infinity, I can say that the max and min are initially 0, because like if the max is less than 0, like we don't need that, because in the beginning the balance is 0, so we can use these values here. But in the segment tree, we can't use that. In the segment tree, we need to have these as the initial conditions. Okay, so now let's try to submit it and see if it is actually correct or not. It might be correct because like so many people got it right. Although I can get it wrong, maybe running for a lot of time, so it's probably wrong, I think. I think it's wrong. Is this a TLE? Could be a wrong answer. What was the time limit anyway? It was 2 seconds. I don't think it should take more than 2 seconds. Just segment tree taking a lot of time. Probably something is wrong, we should fix it. So what I can do is I can first remove this long, then make this infinity a bit smaller. Make it 10 to the power 9. Okay. Okay, so our solution got TLE'd. So I'm removing long. That will probably make it faster. Wait a minute. Is my complexity fine? In each test case, I'm making a segment tree. Then for each query, I'm doing not a lot of work. Yeah, it should be fine, I think. Probably it was just the issue with using long, which I changed now. Still taking a lot of time. Is there an infinite loop somewhere? I don't think it's possible to have an infinite loop in this code. Segment trees, prewritten, then hmm, why is it getting time limit exceeded? This is really strange. Hmm? What's the matter? My code cannot be so slow. Hmm. Oh my god. Oh wow. I did such a stupid mistake. It passed the vector by reference. Right. Okay. Okay, so there was a mistake in my segment tree code. I don't understand why did that not make a problem, cause any problem for so many months. So there was a problem in my segment tree code, and I've been using it for like what 8 months now. No, I've been using it for more than a year, and there was a problem in it, and I didn't know about it. So I need to have these two pass by references in my segment tree somewhere, and I wasn't doing it, and it was working for a year. For a year, my segment tree never caused any problem like this, and there was this issue in it. Anyway, so I'm happy I found that mistake in a unrated contest for me. Anyway, yeah. So the other day also something like that happened to me. That to rewrite that snippet again. Okay, so let's see the number of submissions. Okay, 49 submissions on problem E. That means it's not very easy, but if we do it, then we'll be at a good rank on the leaderboard. Okay, maybe not very good because I think I just got two wrong submissions. Okay, so we're given a weighted and directed graph consisting of n matrices and images. Yeah. What is this? Sum of weights minus max weight plus min weight. Okay. Okay. Hmm. Wow. Okay. So the weight of the path is the sum of the weights minus the maximum plus the minimum. Okay. The minimum will be there twice. The maximum will be there. The maximum won't be there, and the minimum will be there twice. Okay. Hmm. So, like, if we didn't have these, we could have just done a Dijkstra and could have gotten the answer. But we cannot do that because we have these. So, what can we do? So, because we want the minimum weight, I think we can replace any of the edges with the minimum. Okay. Yeah, we can replace any of the edges with the minimum. And I'm saying this because hmm, like if we change each of the edges one by one and get different answers from that, I get the minimum answer when I change the maximum one. So it is obvious that I'll automatically change the maximum one. So here's the thing. I can get from one vertex to another vertex, and like usually I have to add every edge into my answer. But here I can leave one edge out and add the minimum instead. Okay, so yeah, that's the thing. I can leave one of the edges, but add the minimum. Okay, so one edge is actually free. As some kind of magic, I can just perform a jump and not pay anything for one of the edges. But another edge is like has to be traversed twice. Okay, it's something like that. Mhm. Okay, so what if there's just a single edge? So if it's a single edge path, then minimum and maximum will be same, and then it will be equal to that. Okay, I think I get it a little bit. So it's kind of like okay, I have a graph, right? And I have to perform the normal Dijkstra kind of thing. But for each graph, like in the graph, we have normal numbers, right? 1, 2, 3, 4, etc. Here I have the vertices like 1, comma f1, comma f2. Okay. What f1 and f2 mean? So f1 and f2 are two flags. F1 means hmm, I have skipped one. Okay. F2 means I have taken one twice. Okay. And I want to get from my source comma 0 to destination comma 1 comma 1. That's what I want to do. I want to get from source comma. I haven't used any of these two privileges. Actually, one is a privilege and one is the punishment. So I have neither used the privilege nor the punishment. I start from there and I have to do those both and get to this part. And actually, there's no destination, right? I can get from get to all points, right? So yeah, and I want the minimum distance. So the thing is, when I okay, So if I try everything, what will happen is for each path, the best one will be when I skip the maximum and take twice the minimum. Okay, so yeah, that will all automatically be covered. So yeah, I think that's it. Just a simple Dijkstra problem. Okay, so I'll be using Dijkstra's algorithm for this. If you want to learn about it and you are a Hindi speaker, you can attend my Unacademy class that will be held on Saturday. So Saturday 4 p.m. according to Indian time, only for Hindi speakers. Okay, so I have UVW. Waited. This is actually not very difficult. Just with extra with some flags. Okay. So right. I'm pretty sure by the time I do this, there will be a lot of submissions to this because this is not difficult. Okay, so I got the graph as input. Now I have to run the extra. I need an array in which I will store the answers. Okay. So this is vertex comma f1 comma f2. In that I'll store the distances, and I think I need a visited too. Okay, let me just write this code. I'll explain it later because I don't want to mess up while trying to explain it anyway. So okay, I'll make a uh, hmm, set of pair int, and like the first int is for the distance, and then I want something for this vector for this vertex comma flag 1 comma flag 2. Okay. So what I can do is maybe I can just keep a bit mask instead. Will space store some. It will save some space as well. Okay. I can just keep. So it is 2 into f1 plus f2. Okay. I need a pair of int comma parent int. Okay. I'll insert into this. Hmm. What is the? Okay, so from the first vertex. Okay, so from 1 and no flags. Okay, I start here. I mark it visited. Okay, I'll do that later. Okay. So while this set is not empty. Okay. PII. Okay, my eye is straining a bit. Let me just turn off the camera. Okay. So the current pair is like the temp.sc and the distance is temp.fr. Okay. Fine, because that's how I stored it. Distance, comma, the vertex, comma, the 2f1 plus f2. Okay. Now, if visited cur.fr, comma, cur.sc, okay, then I'll just continue. Otherwise, I have to mark it visited. Okay, after that I have to mark the distance of this thing is this is equal to d. Okay, after marking the distance I can, yeah, I can go to the vertices that are adjacent to this. Okay, okay, so it's a bit tricky now. So what I can now, it depends a little bit on the flags. If I turn on both flags at the same time, then I take it once. If I turn on one flag, I'll subtract it once. If I turn on the other flag, I can add it once. Okay, yeah, I think I need the state of the flags as well. So int f1 is equal to car dot sc divided by 2. Then f2 is equal to car dot sc mod 2. Okay, fine. I got both the flags, and let me just define what these flags mean. So I think I did it in my board thing here. Okay, turn on the camera now. Okay, so F1 means I've skipped one, and F2 means I've taken one twice. Okay, so mhm, mhm, mhm. Okay, so yeah, F1 equals skip, F2 equals repick. Okay, fine. So now I have the states of the flags. Okay, let's say I want to go from this state to this state, to the F state. Okay, now if like there can be a problem if like the flag cannot turn off, they can only turn on, right? So if hmm, if f by 2 is smaller than f1, or f mod 2 is smaller than f2, then this is wrong. Okay, so then I'll just continue, otherwise I can go in. Okay, fine. So now I'm going to the state. Oh, wait a minute. So let me just traverse all the edges. PIIX something that is adjacent to cur dot fr. Okay, fine. So now I'll be going to this x dot. Sorry, I'll be going to x dot fr, comma the flag f. Okay, so the flag states f. Okay, so I'm going there. Fine. So yeah, I'll just insert that into the set, right? S dot insert current distance plus the weight. Okay, fine. But this weight will be changed based on the flag that I've changed. Okay, so this will be okay, multiplier will be changed, right? So I'm adding 1. Okay, plus if I change the, I think f2 was repick. Okay, so if I change f2, then this has to be taken twice. So if f mod 2 is greater than f2, then I have to add 1. Otherwise, I'll subtract 1 if f by 2 is greater than f1. Okay, and I think this solves it. Okay, and this was just the one element, the distance. Now for the second element, I have x dot fr, comma the flag. Okay, I think that's it, and now I just have to bring the distances. for int I equals to I smaller equal to n, I plus plus. Okay, so I want to print distance of I comma 3 and put a space, and I think we're done. Okay, so giving me an infinite loop. Why is it doing that? Okay. See, sorry, I didn't erase the set. Okay, so even this can give us a TLE. Wait a minute, are these connected? Okay, we are given a connected graph. Okay, all the test cases passed, and I don't think we need long here as well. So we'll work without that as well. Okay, it's working, and we have 3 seconds, so this should run. Although the time complexity, the running time is somewhere around, like normal Dijkstra is n plus, I think it is n plus m log n, right? So this is more than that. Here I'm multiplying n by 4, so it's becoming 4n plus, I think the edges are also become 4 times, it is 4m and log 4, I think. Maybe the edges are becoming 16 or something. So yeah, it might be up to 32 times the normal Dijkstra. But I think that will still work. It shouldn't give it. Oh, wow, it's a wrong answer. Okay. Fine. So at least that wasn't a TLE, I think. 31 milliseconds. So yeah, we don't have to worry much about the running time. But it's a wrong answer because I removed the definite long. The distance can definitely go beyond uh, our task 32 in bit integer. So I messed up there. Okay, I shouldn't have removed it because like 3 seconds were already enough. There was no issue. There's no way I'll get a TLE. So this wrong answer was due to overflow. I removed the line that I shouldn't have removed. That's fine though. Yeah, it will probably run. I don't have to worry much. And we can go to the F problem right now. It actually is taking a lot of time. Oh wow. Okay, so we got a time limit exceeded here. So we have to fix that. How can we fix that? I think we can use a priority queue instead of a set. Yeah, we can use a priority queue. Okay. Maybe we can make a, yeah, priority queue should work. Okay. Everything will remain the same with priority queue instead. I think this will work. So remove the sets and use the priority queue instead. Q dot push 0 comma 1 comma 0. Okay. Then while Q is not empty, I'll use Q dot top. Okay. then q dot pop and q dot push. Yeah, so priority queue is much faster than a set. Okay, so let me just check if I did this right or not. Yeah, I did it right. Okay. So yeah, this solution should be much faster than the other one in terms of constraints, and I think also in terms of the a bit in terms of complexity, time complexity, because uh, the priority queue can get the biggest element in constant time. Priority queue is better than set for these kind of things. And I think I'll get accepted. Okay. Yeah. So see, it got this one got time limit exceeded on 26, uh, and when the time limit was 3000, and this one got accepted with all of the test cases. I think there were 50, 60 test cases. So this one ran on everything. So yeah, that's the thing. Priority queues are faster. So actually, I did two things. First of all, priority queue is faster. So that's one thing. Other than that, I also made a custom comparator. So in this comparator, I'm not comparing all of the three values. So basically, when you have a pair intent, it contains three values in total. Okay. So what happens is when you compare them, smaller or greater, all three are compared. In this, what I'm doing is I'm comparing only one of the values, one of the three. So that this decreases the time by 1/3 in the first place. Apart from that, priority queue is also faster than the set, so that's why it's running really fast.